Hello folks, so in this video we're going to talk about how we can put together everything we've talked about so far and actually graph one of these more interesting rational functions. Alrighty, so the function we're going to look at is this function right here, r of x equals this cubic on top, and in the bottom we have a quartic or fourth degree polynomial. Alright, and here's what we're going to do. What we're going to do is just like how when you're graphing, say, a parabola or a linear function, you don't go by point, you find a couple important points and get a rough sketch of the graph. So that's what we're going to do in this video. So the important features that we're going to look at are the intercepts. So we're going to find the x and y intercepts, the x-intercept, and the y-intercept. Actually, I'll put the y-intercept first because that one's actually easier to find. So we're going to want to find the x and y-intercepts. There'll only be one y-intercept, excuse me. There could be multiple x-intercepts. We're also going to want to find our removable discontinuities. Again, there might be one or none or multiple. We're going to want to find the vertical asymptotes, if there are any, once again. And last part, we're going to also want to find our horizontal asymptotes. And again, in the last two videos, we talked about how to find our horizontal asymptotes. So 5 components here. And then once we have those, then we're going to draw the rough sketch of the graph. Okay, so the y-intercept, that's pretty easy to find. So all we have to do is plug in x equals 0, just like any other function. So we're going to want to find, I don't know what I just said. We're going to want to find what r of 0 is. What's nice about this, and the cool thing about polynomials is, well, when you plug in 0 for x, everything just cancels out. So you can see here, on the top, you're going to have 0, minus 0, minus 0, minus 15. So we're just going to plug in negative 15 right there in the numerator. And in the bottom, the denominator, we're going to have 0, 0, 0, 0, 0, plus 30. And so our y-intercept is simply going to be at 0, comma, negative 1/2. Okay, the x-intercept is a little bit trickier because now we're trying to find the x values where r of x is actually equal to 0. All right, check this out. Since this is a fraction, we actually don't need to do too much work here, because if I just had this, okay, you have this big funky fraction equals 0, it looks kind of intimidating. But remember this, if you have a fraction, say, I'll just say a over b is equal to 0, the only thing that actually matters is that a equals 0. Again, why is that? Well, remember, the only way to get 0 through division is if you have 0 divided by some number. We also have to keep in mind also that b, this is actually important, and b cannot be 0 at the same time. Because then we have a case we have a 0 over 0, and we talked about, when we're talking about removable discontinuities, that 0 over 0 is actually indeterminate. We can't really figure out what it is. And that's actually going to come up in this video later when we talk about horizontal asymptotes. Okay, so how do I solve this then? Because now, if I'm actually trying to solve this problem, that when is the numerator equal to 0, I'm trying to figure out, okay, well, when is 2x cubed minus 3x squared minus 32x minus 15 equal to 0? That on its own is a pretty hard problem, but this is exactly why we spent so much time trying to factor. Because if I could get this to factor, then I could just use my zero product property. And so, assuming this is factorable, and because this is a scripted problem, it absolutely is factorable, we're going to want to factor it first. So I'm actually going to do that. I'm not going to go through the whole process in the interest of time. So I'm going to pause the video, factor this, and I'll be right back. Alrighty, welcome back. So hopefully you also did that on the side while you were waiting. But I factored this, and this is what I factored it. And we're going to have to factor the bottom anyway, so I did that as well. Okay, so my factors on top, I broke that cubic into x minus 5, 2x plus 1, and then x plus 3. In our denominator, I have x minus 1, x minus 5, x plus 3, and x plus 2. Okay, remember that we're trying to find our x-intercepts, which in short really just boils down to finding when our numerator is equal to 0. So let's go here. So when is our numerator equal to 0? That's what I have A in my little diagram here. Well, I know that my numerator is equal to 0 when I have, well, let's see, if I'm looking at x minus 5, that's going to be when x equals 5, or negative 1/2 for 2x plus 1, or negative 3 when I have x plus 3. Remember, the other important aspect is that the denominator also has to be not 0. And so when is the denominator equal to 0? Well, we can see here that when I have x equals 5, the denominator is also going to be 0, so that's going to be removed from the list. And also when I plug in negative 3 right there. When I plug in negative 1/2, that actually won't make the denominator equal to 0, and so that's our only x-intercept. So in short, you're really looking for factors in the numerator that don't also show up in the denominator. So our one and only x-intercept right here is that x is equal to negative 1/2. Okay? It's right there. Alrighty, moving right along, I'm going to back up a little bit, or back out a little bit. We're looking for our removable discontinuities, if, again, there are any. Remember, we're looking for when do we get 0 over 0. We can, excuse me, we can see this, again, when we have factors that are in the numerator and denominator. So the only factors that get repeated are these two. And again, these are looking for our removable discontinuities. When I plug in x equals positive 5, I'll get 0 over 0. And when I plug in x equals negative 3, I'll also get 0 over 0. So let's say that. When I plug in r of 5, I'll get 0 over 0. When I plug in r of negative 3, we will also get 0 over 0. Now the question is, what is the actual y value of that? Well, now we can kind of simplify this function a little bit. And we can say, I guess I can call it r prime. This is the simplified version of r, where this is almost equal to, again, 2x plus 1 over x minus 1, x plus 2. The reason I'm doing this, again, is to figure out what the function is, quote-unquote, supposed to be when I plug in 5 or negative 3. And again, these will just show up as holes in the graph. So when I plug in, and I'm just going to call this r prime of x, I guess. That's a little apostrophe. Well, I plug in 5. When I plug in negative 3, what will I get? Well, let's see. 2 times 5 plus 1 on top is 11. And in the numerator, or sorry, that's the numerator. In the denominator, I'm going to get 5 minus 1, which is 4, times, maybe I should write this out. 4 times 7, which is 28. So that'll happen at 11 over 28. If I plug in negative 3, I'll get, let's see, negative 6 plus 1. So that'll be at negative 5. And in the denominator, I'm going to get, let's see, negative 4 times negative 1. So positive 4. Like so. Alright, so things are shaping up. We have 2 removable discontinuities at these 2 points right here. Our other aspect, or sorry, one more, and again there's a bunch of pieces here, is to find our vertical asymptotes. Vertical asymptotes. Again, these aren't too bad because we really are just looking for when we want not 0, or when we get not 0 over, let me actually write that out, non-zero over 0. Again, this is going to happen. This is why we factored it, because this makes our life so much easier. The factoring part's honestly the hard part. And I guess the actual sketching of the graph can be a little tricky. When is this going to happen? Well, since our denominator, at the end of the day, again, r of x is roughly equal to this. Again, not counting the removable discontinuities. We're looking at when our denominator is equal to 0, so if I illustrate that in purple, we're going to get x equals positive 1 or negative 1/2. So these are our vertical asymptotes. The last part is our horizontal asymptote right here. And there's only going to be one. I suppose there's a possibility that it could be different depending on if you're going towards positive infinity or negative infinity, but for our cases, at least as of right now, we're just going to assume that they're the same on either end. So again, how do I do this? Well, I'm really just figuring out what's happening to r, what's happening to the y values as you plug in really big values of x. And by big, we mean in magnitude. So that could be at positive infinity or negative infinity. We're going to get the same behavior. So if I plug in a big number here, again, our function is a cubic over a quartic. So I'm going to have, again, 2x cubed minus 3x squared minus 32x minus 15 over this quartic here. And again, this is what I was trying to say in the last video, is that when x is really big, these components don't really matter. And when I say these, I'm talking about the following terms. So in the numerator, these are, again, small, like really small, pretty much negligible compared to 2x cubed. And likewise in the numerator, the denominator, these are again small compared to x to the fourth. And what this lets me say is that when when x is big, this function is effectively really close to just 2x cubed over x to the fourth. And I could actually simplify this to 2 over x. And again, what happens when I take 2, which doesn't grow, it's always just 2, and I divide it by bigger and bigger numbers? Well, the overall fraction just gets smaller and smaller. And so what this means is that these are getting close to 0. And so what we can say is that r of a big number is roughly equal to 0, meaning that y equals 0 is where our horizontal asymptote is going to be. Okay, so that is all the components. In the next video, we're going to take these components and actually use that to help sketch the actual graph. Thanks for watching, and I'll see you in a second.